Tonight, we are going to examine a scientific result that sounds almost impossible. In 2024, a team of physicists published a new kind of warp drive solution. Their equations described a pocket of space that could carry passengers without relying on negative energy, exotic matter, or any substance known only from science fiction. For the first time, the proposed structure satisfied every major classical energy condition used to judge whether a spacetime could exist in the real universe. That claim mattered because energy conditions act like physical guardrails inside general relativity. Einstein's equations can describe many strange arrangements of space and time, but some of those arrangements demand matter with properties that have never been observed on a useful scale. Earlier warp drives crossed those guardrails. This new model was designed to remain inside them. The paper was written by Jared Fuchs and a team of researchers working with applied physics. It appeared in the journal Classical and Quantum Gravity, where the original Alcubierre warp drive paper had helped begin the modern discussion 3 decades earlier. Headlines quickly suggested that scientists had finally discovered a genuine path toward faster-than-light travel. And it is easy to understand why. The nearest star system sits more than 4 light-years away. Even Voyager 1, moving at tens of thousands of miles per hour, would need roughly 70,000 years to cross a similar distance. Chemical rockets cannot solve that problem. Fusion engines, laser sails, and antimatter might shorten the journey, but none of them remove the speed limit built into relativity. A warp drive offers a completely different possibility. Instead of forcing a spacecraft through space at impossible speed, it would reshape the space surrounding the craft. The passengers could remain inside a calm region of nearly flat spacetime, while the geometry around them carried the vessel forward. In the 2024 model, the passenger region was surrounded by a thick spherical shell of positive mass. The shell created a powerful gravitational field, while a carefully arranged flow of momentum produced the warp-like motion. Far outside the shell, space-time returned toward its ordinary shape. Inside, the central cavity remained protected from the most extreme curvature. This was still a mathematical construction rather than a machine. It contained no reactor, no manufacturing process, and no instructions for assembling the shell. But it passed tests that earlier warp geometries had failed. In the technical language of the paper, the model possessed positive total mass and satisfied the weak, null, strong, and dominant energy conditions. That is not merely a science fiction idea. Valid warp geometries have appeared in Einstein's equations since 1994. But every earlier design required something nature may not permit. The new solution appeared to remove that obstacle. There was only one problem. Buried inside the paper was a single word that changed the meaning of the entire discovery: subluminal. The word means slower than light, although the full consequence of that limit becomes clear only when the model is compared with the distances between stars. And once physicists examined the numbers, they found that the proposed drive would need a shell containing more than twice the mass of Jupiter, compressed into a region only a few dozen meters across. The inner cavity had a radius of about 10 meters. The shell extended to roughly 20 meters. Its calculated mass was approximately 4.49 times 10 to the 27 kilograms. The numerical example also used a warp parameter equal to about 4% of light speed. That is thousands of times faster than today's interstellar probes, yet it remains far below the velocity promised by the phrase faster than light. The result therefore sits in an unusual place. It is more physically acceptable than the famous warp bubbles that came before it, while remaining vastly beyond any technology humanity can imagine constructing. It brings warp geometry closer to ordinary matter without bringing the nearest star close enough for an ordinary human journey. So, have scientists discovered a real way to travel faster than light? Or have they created the most physically realistic warp drive yet? only to find that the speed of light remains exactly where it has always been. Before we continue, take a moment to subscribe if you enjoy calm journeys through the deepest questions in space and physics. Now, let us begin with the barrier every warp drive is attempting to escape. Proxima Centauri provides the simplest test of what the new warp geometry could accomplish. It is the nearest known star beyond our solar system, located about 4.25 light-years from Earth. Proxima belongs to the wider Alpha Centauri system, along with Alpha Centauri A and Alpha Centauri B. It is a small red dwarf, faint enough to remain invisible to the unaided eye despite being our closest stellar neighbor. A light-year measures distance. It is the distance light crosses through a vacuum during 1 year, moving at nearly 300,000 kilometers every second. 1 light-year equals about 9.46 trillion kilometers. Multiplying that by 4.25 places Proxima Centauri roughly 40 trillion kilometers away. That number becomes easier to understand when it is turned into travel time. Voyager 1 left Earth in September of 1977. After flying past Jupiter and Saturn, it continued outward and eventually entered interstellar space. It now moves at roughly 17 kilometers per second relative to the Sun as it travels away from the planets. At that speed, covering the distance to Proxima Centauri would require about 75,000 years. Voyager 1 is aimed toward a different region of the sky. The comparison simply applies the speed of a real interstellar spacecraft to the nearest stellar distance. 75,000 years reaches far beyond every city and written language that exists today. The earliest known writing systems appeared a little more than 5,000 years ago. Agriculture began in several regions, roughly 10,000 to 12,000 years ago. A Voyager speed mission launched when farming first appeared would still have most of its journey ahead of it. Ordinary improvements in velocity shorten the trip, although the distance absorbs those gains with surprising ease. Traveling 10 times faster than Voyager, one would still require about 7,500 years. At 100 times Voyager's speed, the crossing would take approximately 750 years. A machine moving at 1% of light speed, almost 3,000 kilometers per second, would arrive after about 425 years. Those speeds already exceed anything available for a large spacecraft. Parker Solar Probe holds the human speed record. Near its closest approaches to the Sun, it has traveled at approximately 190 kilometers per second. Parker reaches that velocity by repeatedly passing Venus and falling deep into the Sun's gravitational field, where gravitational potential energy becomes motion. The probe reaches its record speed near the bottom of that fall, then slows as it climbs outward again. Parker's record represents a brief part of a curved solar orbit, rather than a steady cruise toward another star. Its path keeps it close to the Sun, and applying 190 kilometers per second to the distance of Proxima Centauri would still produce a journey of roughly 6,700 years. Different missions can accept different versions of that delay. A gram-scale robotic probe has no crew to feed, shield, or return home. The proposed breakthrough Starshot concept would use powerful ground-based lasers to accelerate tiny sailcraft toward perhaps 20% of light speed. In the ideal version, a probe could pass through the Alpha Centauri system after a little more than 20 years. Its signal would then need another 4.25 years to reach Earth. Crewed vessels carry a larger burden. Food production, air recycling, radiation shielding, repairs, medicine, and social stability must continue throughout the voyage. A generation ship traveling at 1% of light speed would need to support human life for more than 4 centuries. The people who arrived would be separated by many generations from those who selected the destination. Faster-than-light travel promises a different kind of interstellar future. Distance could be crossed without turning every mission into an inheritance passed through families or a message delivered long after its senders had died. Proxima Centauri is called our nearest stellar neighbor, yet present spacecraft speeds place it beyond time, spans longer than recorded civilization. Increasing velocity appears to offer the direct solution. Near light speed, however, energy stops rising in the familiar straight line, and each additional gain becomes harder than the one before it. At everyday speeds, that difficulty is easy to underestimate. A car given more energy moves faster, and a rocket with more propellant can leave Earth at a higher velocity. This familiar relationship continues through an enormous range of speeds. Near the speed of light, the pattern changes. Albert Einstein described the reason in 1905 in a paper titled On the Electrodynamics of Moving Bodies. The theory that grew from it became known as special relativity. It began with two connected principles. The laws of physics should have the same form for observers moving steadily relative to one another, and every such observer should measure the same speed of light in a vacuum. An observer moving steadily without turning or accelerating is called an inertial observer. A person standing beside a laboratory and a person coasting past it in a spacecraft can disagree about the spacecraft's speed. They will still measure a passing beam of light at approximately 300,000 kilometers per second. Space and time adjust to preserve that result. A moving clock accumulates less elapsed time when compared with a clock that later reunites with it. Distances measured along the direction of motion become shorter. Observers can also disagree about whether two separated events happened at the same moment. These effects are known as time dilation, length contraction, and the relativity of simultaneity. They have been measured many times. Muons provide one clear example. These unstable particles form high in Earth's atmosphere when cosmic rays strike atomic nuclei. A muon at rest survives for an average of about 2.2 millionths of a second before decaying. Many atmospheric muons move close enough to light speed that time dilation allows them to reach detectors at ground level in numbers far greater than classical calculations would predict. The strength of these relativistic effects is described by the Lorentz factor. At 90% of light speed, the factor is about 2.29. A year experienced during steady cruise would correspond to roughly 2.29 years in the original rest frame. At 99% of light speed, the factor rises to about 7.09. At 99.9%, it reaches about 22.4. The velocity changes by less than 10 percentage points across those examples. The Lorentz factor increases almost tenfold. Energy follows the same factor. The rest mass of a spacecraft remains constant. Its total energy and momentum rise more sharply as its velocity approaches light speed. For a 1 kilogram object, reaching 90% of light speed would require about 1.16 times 10 to the 17 joules of kinetic energy. That is roughly the energy released by 28 million tons of exploding TNT applied to an object with the mass of a bottle of water. A crewed spacecraft would weigh many thousands of tons before fuel, shielding, life support machinery, and supplies were included. Accelerating it would require vastly more energy, followed by a similar requirement for slowing it near the destination. Collisions with dust and gas would also become increasingly energetic as the craft moved faster. Particle accelerators reveal the boundary directly. At the Large Hadron Collider near Geneva, protons circulate through a ring about 27 kilometers around. Powerful magnets guide them, while radio frequency cavities add energy during repeated passes. At energies of several trillion electron volts per proton, they move above 99.999999% of light speed. Additional energy still changes their momentum and makes their collisions more powerful. Their speed increases by only a minute amount. No matter how much energy is supplied, a particle with non-zero rest mass remains below light speed. Reaching the boundary would require the Lorentz factor, momentum, and energy to grow without limit. This makes light speed an asymptotic boundary. An asymptote is a value that can be approached ever more closely without being reached through the same process. Stronger fusion engines, antimatter systems, or laser sails could move a spacecraft nearer to that boundary. Ordinary acceleration offers no final step through it. The restriction applies to local motion through spacetime. General relativity would reveal that the geometry carrying that motion has freedoms of its own. That wider freedom emerged 10 years after special relativity, when Einstein completed the general theory of relativity in 1915. Special relativity describes observers moving through regions where gravity can be ignored. General relativity includes gravity by changing the way space and time are understood. They form a flexible geometry whose shape depends on matter, energy, pressure, and momentum. The mathematical rule describing that geometry is called the metric. A metric determines how distances and time intervals are measured within a particular spacetime. On a flat sheet, the shortest distance between 2 points is a straight line. On the curved surface of Earth, the shortest route follows part of a great circle. General relativity extends this idea into 4 dimensions, combining 3 dimensions of space with time. Objects moving freely follow the most direct available paths through that geometry. These paths are called geodesics. Earth follows a geodesic around the Sun because the Sun's mass curves the surrounding spacetime. The planet requires no invisible cord holding it in orbit. Its path bends because the geometry through which it moves is already curved. Light follows the same geometry. During a total solar eclipse in May of 1919, astronomers photographed stars appearing close to the darkened Sun and compared their positions with photographs taken at another time of year. The apparent shift supported Einstein's prediction that light passing near a massive object would be deflected. Modern telescopes observe much stronger examples. A massive galaxy or galaxy cluster can bend light from a more distant object into stretched arcs, repeated images, or nearly complete rings. This effect is called gravitational lensing. Astronomers use it to map otherwise invisible matter and magnify galaxies located billions of light years away. Time also responds to gravity. A clock deeper in a gravitational field runs more slowly relative to one farther away. This difference is small near Earth, yet precise enough to affect the global positioning system. Navigation satellites orbit about 20,200 kilometers above Earth. Their motion makes their clocks run slightly slower through special relativity, while the weaker gravity at their altitude makes them run faster through general relativity. The combined difference is approximately 38 millionths of a second per day. Without regular relativistic corrections, position errors would accumulate by kilometers. Rotating objects produce another effect called frame dragging. A spinning mass slightly twists the space-time around it. NASA's Gravity Probe B mission, launched in 2004, and carried 4 exceptionally precise gyroscopes into polar orbit. Changes in their orientation were used to measure both Earth's large-scale curvature and the much smaller dragging caused by the planet's rotation. Spacetime can also carry waves. On September 14, 2015, the Laser Interferometer Gravitational Wave Observatory recorded a brief signal produced by 2 black holes merging about 1.3 billion years earlier. The passing wave changed the lengths of 2 perpendicular detector arms by less than the width of a proton. The measurement provided direct evidence that changing curvature can travel across the universe. These examples show that geometry participates in physical events. It guides planets, bends light, changes clock rates, twists around rotating matter, and carries gravitational radiation. The local speed of light remains fixed throughout these effects. An observer beside a passing beam still measures it traveling at exactly 299 million, 792,458 meters per second in a vacuum. Measurements made across enormous regions can behave differently. The distance between two faraway galaxies can increase because the large-scale metric of the universe changes with time. Cosmologists describe this using the cosmic scale factor, a number that tracks how distances between widely separated, unbound regions grow as the universe expands. At sufficiently great distances, this expansion can increase the separation between galaxies by more than 1 light-year during a single year. Their recession rate can therefore exceed light speed. Each galaxy still sees nearby light moving normally, and neither galaxy locally races through its surrounding space beyond the relativistic limit. Models of cosmic inflation extend this behavior into the earliest fraction of the universe's history. During inflation, the scale factor may have increased extremely rapidly, stretching microscopic variations into structures that later influence the distribution of galaxies. Cosmic expansion provides evidence that relativity permits dramatic changes in geometry. It offers no known machine for producing such changes around a spacecraft. The expansion observed between distant galaxies is also extraordinarily weak across the scale of a solar system, where gravity and other forces hold matter together. Warp drive research begins from this narrow distinction. A spacecraft cannot be accelerated locally through the speed of light. A carefully chosen metric might carry a compact region by changing the geometry around it. In 1994, a physicist named Miguel Alcubierre calculated what such a moving region would look like inside Einstein's equations. Miguel Alcubierre approached the problem by designing the journey directly into the geometry. In 1994, while studying general relativity at the University of Wales in Cardiff, the Mexican physicist published a short paper in the journal Classical and Quantum Gravity. Its title was The Warp Drive: Hyper-Fast Travel Within General Relativity. The idea was partly inspired by the fictional warp engines used in stories such as Star Trek, although the calculation itself remained inside Einstein's field equations. Alcubierre described a metric, which is the mathematical rule used to measure distance and time throughout a spacetime. He selected a geometry that contained a compact region moving through an otherwise ordinary universe. This region later became known as the warp bubble. The geometry can be divided into 3 broad areas. Near the center, space-time remains almost flat. A spacecraft and its passengers could occupy this protected interior without sitting directly inside the strongest curvature. Far outside the bubble, the geometry approaches ordinary flat space-time again. The dramatic changes are concentrated within a wall, separating those 2 regions. That wall is arranged so that distances ahead of the bubble become smaller, while distances behind it become larger. A destination in front is brought closer through contraction, while the point of departure recedes through expansion. The central region is carried along with the changing geometry. Popular illustrations often show this as a stretched grid, compressed in front of a spacecraft and widened behind it. The real calculation describes changes in measured intervals rather than a visible fabric. The grid remains a useful way to picture how the distance between locations can change without the spacecraft locally crossing the space between them at an impossible speed. An important part of the metric is called the shift vector. It describes how spatial coordinates slide between one moment and the next. In Alcubierre's solution, the shift is arranged so that the center of the bubble moves through the external coordinate system. The spacecraft stays near the same position inside its local bubble. Its motion relative to distant stars comes from the changing coordinate geometry surrounding it. A simple comparison would be a person standing on a moving walkway. The walkway changes the person's position relative to the building, even while the person remains at rest relative to the surface beneath their feet. The warp metric extends that basic idea into space-time itself, with geometry taking the role of the moving surface. At the exact center of the idealized bubble, a passenger follows a geodesic. A geodesic is the natural path taken by an object in freefall through curved spacetime. Earth follows a geodesic around the Sun, and astronauts in orbit follow geodesics around Earth. Following a geodesic means the passenger does not require continuous local thrust to remain on that path. An accelerometer carried at the bubble's center would ideally register no sustained acceleration, even while distant observers saw the entire region changing position. The passenger's proper time also passes normally in the original construction. Proper time is the time measured by a clock traveling with the observer. Alcubierre chose the central geometry so that the passenger's clock could remain closely aligned with the external coordinate time used in the model. The extreme relativistic time dilation associated with an ordinary spacecraft moving near light speed would therefore be absent at the center of this ideal bubble. The effective speed of the bubble was not limited in the same way as the local speed of a material spacecraft. Alcubierre's equations allowed the center of the region to move through the external coordinates at any chosen rate. At sufficiently high values, the bubble could connect two distant locations in less time than light would need to cross the unchanged space between them. Every nearby beam of light would still move locally at the normal speed of light. The passengers would also remain below that speed relative to the space-time immediately surrounding them. The shortened travel time came from the geometry changing around the bubble. This gave faster-than-light travel a clear mathematical form. The paper described the interior, the moving wall, and the external space-time in a single solution to general relativity. Engineering instructions remained outside its scope. The metric did not explain how to create the bubble, assemble its wall, or supply the required source of curvature. When Alcubierre inserted the geometry into Einstein's field equations, the resulting stress-energy tensor revealed exactly what the bubble wall would demand from matter and energy. The calculation worked because Einstein's field equations can be read in two directions. Physicists usually begin with matter and energy, then calculate how they curve the surrounding space-time. Alcubierre began with the geometry he wanted and worked backward to learn what would have to produce it. One side of the field equations describes curvature. It records how space-time bends, stretches, and changes from place to place. The other side contains a quantity called the stress-energy tensor. A tensor is a mathematical object that can hold several related measurements at once. In this case, it keeps track of energy density, pressure, internal stress, and the flow of momentum through a region. Gas clouds have positive energy density and pressure. Beams of light carry energy and momentum in the direction they travel. Neutron stars reach far greater densities, allowing a body only about 20 kilometers wide to contain more mass than the Sun. The same equations can describe sources with much stranger properties. General relativity contains no built-in catalog limiting every solution to steel, plasma, radiation, or any other material already observed. When a researcher chooses an unusual geometry, the calculated source may demand negative energy density or extreme pressure. Some solutions also require energy to flow in ways that ordinary matter cannot reproduce. Physicists use energy conditions to judge these results. They are broad tests applied to the stress-energy tensor. Each condition examines whether the source remains reasonably consistent with familiar matter and causal energy flow. One of these filters, the weak energy condition, considers an observer traveling below light speed through the region. Such a path is called time-like because a clock can move along it and record ordinary elapsed time. The condition requires every permitted time-like observer to measure an energy density of 0 or greater. Light follows a different category of path called null. A null path has 0 space-time interval, which is a special geometric property of light in relativity. The null energy condition applies a related test along these light-like directions. It plays an important role in many results involving gravitational focusing, black holes, and wormholes. Energy flow is covered by the dominant energy condition. This restriction is designed to prevent energy from behaving as though it carries usable influence faster than light. The strong energy condition concerns the way gravity focuses nearby paths through spacetime, although some real cosmological systems do not satisfy it. Energy conditions remain valuable tests without serving as absolute laws at every scale. Quantum fields can produce small, temporary violations under carefully controlled circumstances. The accelerated expansion of the universe is also associated with pressure that fails some classical conditions. Ordinary classical matter usually behaves within these boundaries, while large violations often signal that a proposed geometry requires unfamiliar physics. When Alcubierre calculated the source for his bubble, observers moving normally with the surrounding spatial coordinates measured negative energy density within parts of the wall. The required material would contain less energy than the chosen vacuum reference in those regions. The weak energy condition failed there, and the null energy condition was violated as well. The negative energy was arranged around the bubble instead of filling the calm central cavity. In three-dimensional descriptions, the strongest requirement forms a ring-like region around the direction of travel. This shape is often described as a torus, meaning a form similar to a thick ring. Its total requirement depends on the size and speed of the bubble. Wall thickness also matters greatly. A sharper boundary concentrates stronger changes in curvature into a smaller distance, increasing the magnitude of the stress energy needed there. This result left Alcubierre's metric mathematically consistent. The field equations successfully connected the chosen geometry with its required source. Physical construction presented the unsolved problem. No known technology can manufacture or store macroscopic negative energy, much less arrange it into a stable moving shell around a spacecraft. Quantum field theory nevertheless contains limited situations in which measured energy can fall below a vacuum reference. Those small effects would soon become the focus of attempts to determine whether Alcubierre's material requirement was forbidden by nature or simply far beyond anything humanity had learned to control. Those limited effects begin with a careful definition of energy. Negative energy is often confused with antimatter. Antimatter particles carry charges opposite to those of their ordinary counterparts. A positron has the same mass as an electron and a positive electric charge. When matter and antimatter meet, their mass energy can become radiation. Both sides of that reaction still contain positive energy. Dark matter also behaves as positive mass. Astronomers infer its presence from the motion of stars inside galaxies, the bending of distant light, and the way large cosmic structures formed. Its identity remains unknown, although its gravity attracts ordinary matter in the familiar direction. Negative energy density belongs to a different part of physics. It describes a region whose measured energy falls below a chosen reference level. In quantum field theory, that reference is often the vacuum state, which is the lowest energy condition available to a field under a particular set of boundaries. The word vacuum can be misleading. A laboratory vacuum contains very few ordinary atoms, yet quantum fields still extend through it. The electromagnetic field remains present even when no photons are detected. Its ground state retains unavoidable fluctuations because certain pairs of physical quantities cannot both be fixed with perfect precision. These fluctuations are sometimes described as particles briefly appearing and borrowing energy. That image can be useful in informal explanations, although the actual theory is built from quantum fields and their allowed states. No temporary loan account exists in the equations. The measurable effects come from how those fields respond to boundaries, motion, and space-time geometry. One of the clearest examples was proposed in 1948 by the Dutch physicist Hendrik Casimir. Casimir considered two uncharged conducting plates, placed extremely close together in a vacuum. Conducting surfaces restrict the electromagnetic field. Between the plates, only field patterns with wavelengths that fit the narrow gap are allowed. Outside them, a wider range of patterns remains available. This difference changes the field's energy. The configuration produces a small attraction between the plates, now called the Casimir force. As the separation decreases, the force rises sharply. In the ideal parallel plate calculation, its strength varies approximately with the inverse fourth power of the distance. Cutting the gap in half can therefore increase the pressure by about 16 times. The effect is still extremely small at everyday scales. At a separation near 1 micrometer, or 1,000th of a millimeter, the predicted pressure is only around 1,000th of a pascal. A pascal is 1 newton of force spread across 1 square meter. Bringing the surfaces closer makes the force easier to detect, although maintaining clean, parallel plates at those distances becomes difficult. Early experiments struggled with surface roughness, electrical contamination, and alignment. More precise measurements arrived during the 1990s. In 1997, Stephen Lamoureux measured the force using a torsion pendulum and curved conducting surfaces. Later experiments used atomic force microscopes and microfabricated devices at separations of a few hundred nanometers. A nanometer is 1/1000th of a meter. Human hair is often between 50,000 and 100,000 nanometers wide, making the experimental gaps hundreds of times narrower than a strand of hair. The Casimir configuration can be described as having a lower electromagnetic vacuum energy between the surfaces than in the surrounding region. In that limited sense, the energy density is negative relative to the outside vacuum reference. This does not create a piece of material with negative mass. The complete apparatus includes the plates, the forces holding them apart, and the energy needed to build and position them. Its total energy remains positive. The small sub-vacuum region also disappears when the boundary conditions are removed. An Alcubierre bubble demands something far more extensive. Negative energy would need to occupy a carefully shaped three-dimensional wall around a spacecraft. The distribution would have to remain stable while the bubble moved, and its strength would need to produce large changes in spacetime across distances measured in meters. Laboratory Casimir systems operate across gaps measured in billionths or millionths of a meter. Their forces are detectable with sensitive instruments, yet they provide no known method for filling a spacecraft-sized shell with movable negative energy. The Casimir effect, therefore, establishes a narrow physical possibility. Quantum fields can fall below a vacuum reference under specific boundary conditions. Nature also limits how intense such a region can become, how long it can persist, and how widely it can spread. The limits became clearer in 1997, when physicists Michael Fenning and Larry Ford applied quantum inequalities to Alcubierre's original geometry. A quantum inequality is a mathematical restriction on negative energy. It allows a quantum field to dip below its vacuum reference while limiting the depth and duration of that dip. A weak, negative energy region may persist longer. A much stronger region must disappear more quickly. The restriction is measured along an observer's path through spacetime. Physicists imagine the observer carrying an ideal detector and averaging the energy encountered during a chosen sampling interval. The sampling process belongs to the mathematics of the field, rather than the limits of a real instrument. If the measured energy becomes strongly negative, the permitted sampling interval becomes extremely short. Extending the effect through a larger distance creates a similar difficulty because an observer spends more time crossing the region. This trade-off causes trouble for a warp bubble. The bubble wall must surround a cavity large enough to hold a spacecraft. Its negative energy must remain present during the entire journey. and the distribution must move while preserving a carefully chosen shape. The curvature also needs to be strong enough to produce meaningful contraction and expansion around the passenger region. Fenning and Ford considered what an observer would measure while passing through the wall. A thick wall would expose the observer to negative energy for too long. Making the wall thinner shortens the exposure, although the geometry then changes across a smaller distance. That sharper change demands more intense curvature and a greater negative energy density. The two effects reinforce each other. The quantum restriction favors a brief encounter, while the warp geometry becomes more extreme as the encounter is compressed. Under the assumptions used in their analysis, a macroscopic Alcubierre bubble could require a wall only a few hundred Planck lengths thick. The Planck length is approximately 1.616 times 10 to the minus 35 meters. It is formed from three constants that appear throughout fundamental physics: the speed of light, Newton's gravitational constant, and the reduced Planck constant used in quantum mechanics. A few hundred Planck lengths would produce a wall thickness near 10 to the minus 33 meters. A proton is roughly 10 to the minus 15 meters across. The permitted warp wall would therefore be around 18 orders of magnitude smaller than a proton. That difference is difficult to picture. Dividing the width of a proton by the proposed wall thickness produces a ratio comparable to dividing the distance across a continent by a distance smaller than an atomic nucleus. The challenge extends beyond manufacturing precision. General relativity treats spacetime as a smooth geometry. That description works across the scale of planets, stars, black holes, and the expanding universe. Near the Planck scale, quantum effects are expected to influence spacetime itself. Physicists do not yet possess a complete, experimentally confirmed theory describing that regime. General relativity explains gravity and large-scale geometry. Quantum mechanics explains particles and the other known forces with extraordinary accuracy. Combining both descriptions at the smallest meaningful distances remains one of physics' central unfinished problems. A wall, only a few hundred Planck lengths thick, would sit inside that uncertain territory. Calculating it with a smooth classical metric may resemble drawing a continuous line through a region where spacetime no longer behaves continuously. The total energy requirement also remained immense. Compressing the negative energy into a thinner wall did not turn it into a modest laboratory effect. It concentrated an already extreme source into a smaller volume while demanding control at a scale far beyond known matter. The 1997 result did not prove that every possible warp geometry must fail in exactly the same way. It applied quantum inequalities to Alcubierre's particular construction under stated assumptions. Its conclusion still revealed a severe conflict between a spacecraft-sized bubble and the known limits of quantum fields. The original geometry had placed the negative energy in a broad mathematical arrangement around the craft. Researchers could alter that arrangement. Changing the bubble's exterior size, internal volume, or wall profile might reduce the total amount required. The next phase of warp drive research therefore focused on reshaping the bubble itself, searching for a geometry that could shrink the physical cost without losing the protected region at its center. The first major redesign appeared in 1999, when Belgian physicist Chris van den Broek changed the relationship between the bubble's interior and exterior. Alcubierre's original construction surrounded the passenger region with a wall whose outer size was comparable to the useful space inside it. Van den Broek proposed an unusual geometry with a very small exterior surface and a much larger internal volume. From a distant viewpoint, the structure could occupy a microscopic region. Inside that outer boundary, curved spatial geometry opened into a cavity large enough to hold passengers. The arrangement resembles the way a small entrance in a drawing might lead into a room whose measured interior is much larger than the doorway suggests. General relativity allows this mismatch because interior volume depends on the metric. Ordinary intuition assumes that a container's external dimensions determine how much space it holds. Curved geometry can change that relationship. The modification mattered because most of the extreme stress energy was concentrated near the bubble wall. The total requirement is found by adding, or integrating, the energy density across the entire wall. Reducing the effective outer surface reduces the amount of space that must contain the most extreme curvature. Van den Broek's calculations lowered the total negative energy estimate by an enormous number of orders of magnitude compared with early interpretations of the Alcubierre design. Some previous estimates reached far beyond the mass energy of galaxies. The revised values moved toward quantities comparable to several stars. That reduction represented real mathematical progress. Several stellar masses of negative energy would still exceed anything humanity could create, collect, or control. The model also paired the small outer region with extremely strong curvature, making the transition into the large interior physically severe. Construction would require arranging the metric with extraordinary precision. Matter placed slightly away from its required location would create a different gravitational field. A usable design would also need a way to form the enlarged interior while keeping the surrounding geometry stable. The geometry itself had become more efficient, while its required material remained exotic. Further work showed that the familiar picture of compressed space ahead and expanded space behind was only one member of a wider family. In 2002, Portuguese physicist José Notario published a warp drive model with zero expansion. In relativity, expansion measures how the volume of a small group of neighboring paths changes over time. Notario arranged the shift field so that local volumes could remain unchanged while different parts of the geometry still moved relative to one another. The motion was produced through shear. Shear changes the shape of a region by sliding neighboring parts in different directions, much as a rectangular deck of cards can become slanted while keeping the same total volume. This result widened the mathematical definition of a warp drive. A moving passenger region did not always require a simple area of expansion behind it and contraction ahead of it. Other patterns of spatial flow could produce similar effective transport. The energy problem survived. Notario's superluminal construction still violated the relevant energy conditions. Changing the description of the motion altered the distribution of stress and curvature without supplying a known physical source. During the following decade, aerospace engineer Harold White explored additional changes to the Alcubierre geometry through work associated with NASA's Johnson Space Center in Houston. His studies examined ring-shaped or toroidal energy distributions around the craft. He also investigated how changing the thickness and intensity profile of the bubble wall could affect the calculated total energy. Some public presentations produced estimates involving mass equivalents of several hundred kilograms under highly optimized assumptions. Those figures were repeated widely because they transformed an astronomical quantity into something comparable to a car. The calculation depended strongly on the selected wall shape, bubble size, field intensity, and mathematical profile. It provided no demonstrated material capable of generating the required stress energy. The underlying superluminal geometry continued to involve negative energy, and no complete process showed how the ring could be assembled or maintained. These revisions revealed an important feature of warp metrics. Small geometric changes can alter the integrated energy requirement by many orders of magnitude. A lower number can remain physically unreachable when its sign is negative, its density is extreme, or its distribution requires control below known material scales. By this point, researchers had learned to reshape the bubble, reduce its outer area, and distribute its curvature in new ways. A supplied bubble would still need to receive instructions during flight. At superluminal speed, the leading wall can move beyond the reach of every signal sent from the passengers inside. Inside such a bubble, navigation would depend on communication with the curved walls surrounding the passenger region. A pilot changing course would need to alter the stress-energy distribution ahead of the craft. Slowing down would require the leading and trailing parts of the geometry to change in a coordinated way. Arriving safely would also require the bubble to dissolve at the correct location without releasing dangerous amounts of stored energy. At speeds below light, signals sent from the central cabin may still reach every part of the wall. A radio pulse, laser beam, or other influence can travel outward through the interior and eventually arrive at the leading boundary. The wall can remain within the passenger's causal future, meaning an action taken inside the craft can still affect it later. The geometry changes once the bubble moves through the external coordinates faster than light. Imagine that the leading wall is receding from the cabin at an effective speed greater than any signal can cross the intervening spacetime. A beam of light sent forward continues moving locally at exactly the normal speed of light, yet the changing geometry carries the destination boundary away even faster. The signal never reaches it. This creates a horizon. A horizon is a boundary separating events that can exchange information from events that cannot. Earth's oceans create visual horizons because the planet is curved, although light from beyond them can still reach an observer after traveling through the atmosphere. A causal horizon is more fundamental. Signals emitted on one side cannot influence certain events on the other side, even with perfect equipment and unlimited transmission power. Black holes contain the most familiar example. Once an object crosses an event horizon, every future directed path available to it leads farther inward. The warp drive horizon is produced by a different geometry, but the practical result is related. Part of the bubble wall lies beyond the reach of commands issued from the passenger region. A control panel inside the cabin could still operate local equipment. It could display clocks, monitor the interior, and communicate with systems that remained causally connected. It could not send a new instruction to a forward wall that no outgoing light signal could reach. The destination would therefore need to be encoded into the spacetime before the superluminal phase began. The bubble's speed profile, route, and stopping conditions might all have to be prepared in advance. Creating the bubble presents the same difficulty from the opposite direction. The original Alcubierre solution describes a completed geometry moving through spacetime. It does not show an ordinary spacecraft switching on a machine and producing the entire superluminal wall around itself. Some analyses suggest that the required fields would need to be arranged from outside the passenger region. Matter or energy might have to be distributed along the intended route before departure. A mechanism waiting near the destination could then alter the approaching geometry or cause it to collapse at a planned time. Such a system would resemble a railway built through spacetime more than an independently piloted spacecraft. The traveler could enter a prepared route, while the important control decisions were made by infrastructure placed outside the bubble. Installing that infrastructure would require slower than light travel. A probe would first need to cross the distance conventionally, carrying equipment capable of shaping spacetime at the far end. Reaching Proxima Centauri at Voyager 1's speed would still take around 75,000 years. Even a probe traveling at 20% of light speed would need more than 20 years to arrive, followed by the time required to construct and test whatever machinery the route demanded. A prepared corridor could eventually allow later travelers to move more quickly. The first path would still be established without the benefit it was meant to provide. Navigation errors would also become difficult to correct. A change in the destination star's motion, an unexpected object along the route, or a small error in the original field configuration could not be handled through an immediate command from the cabin. The passengers would follow a trajectory shaped before the horizon formed. The calm interior would hide a profound operational weakness. The people inside might feel no continuous acceleration and see no violent motion, yet the structure carrying them would no longer respond like a vehicle under human control. Horizons also interact with quantum fields. Light and other field disturbances can become stretched, compressed, or trapped near their boundaries. In a dynamically created superluminal bubble, those effects may grow strong enough to threaten the stability of the geometry itself. A useful warp drive would need a history. It would begin in ordinary spacetime, form around a spacecraft, maintain its shape during travel, and eventually dissolve near the destination. Alcubierre's original calculation described a completed geometry. It did not show how that geometry developed from an earlier, ordinary state. This distinction became important in 2009, when physicists Stefano Finazzi, Stefano Liberati, and Carlos Barcelo studied quantum fields inside a dynamically created superluminal warp drive spacetime. Their approach used semi-classical gravity. In this framework, spacetime is still described by the smooth geometry of general relativity. Quantum fields are then allowed to move through that curved background. Researchers calculate the energy produced by those fields and examine how strongly it could affect the geometry. Semi-classical gravity is also used when studying Hawking radiation around black holes. It does not provide a complete theory of quantum gravity, although it can reveal places where a classical spacetime becomes unstable once quantum effects are included. The researchers considered a bubble that began below light speed and later accelerated into a superluminal state. As the effective speed increased, the causal structure changed. Two important boundaries formed. The first shared some features with a black hole horizon. Light, traveling forward from behind this boundary, could fail to escape through it. The second resembled a white hole horizon, where light and other disturbances could leave but could not enter from the opposite direction. These comparisons concern the behavior of signals. The bubble did not contain a collapsed star or a conventional black hole. Its changing geometry created boundaries with similar causal properties. Quantum fields respond strongly to horizons because the meaning of empty space depends partly on how field modes are divided between different observers. A mode is one allowed pattern of vibration in a quantum field. Near a horizon, those patterns can be stretched across enormous wavelength ranges or compressed into very short ones. The process mixes what different observers classify as empty vacuum and what they classify as particles. Around a black hole, this mixing leads to the thermal emission known as Hawking radiation. Finazzi and his colleagues found a related effect inside the warp geometry. An observer near the center could receive a thermal flux, whose temperature depended on the details of the horizon and the bubble's acceleration history. The analysis also revealed a more severe problem near the white horizon region. There, the calculated quantum stress energy could grow rapidly with time. The relevant quantity was the renormalized stress energy tensor. Renormalization is the mathematical procedure used to remove the infinite vacuum terms that appear in quantum field calculations, leaving the finite differences that can influence physical measurements. In the model, this remaining energy became increasingly concentrated near the white horizon. The growth was exponential, meaning it increased by repeated multiplication rather than by a fixed amount during each interval. Even a small initial contribution can become enormous under exponential growth. A quantity doubling every second becomes more than 1,000 times larger after 10 seconds and more than 1 million times larger after 20 seconds. The exact timescale for a warp bubble would depend on its size, speed, and detailed geometry. The important result was the direction of the feedback. The horizon generated quantum stress energy, and that stress energy would contribute to space-time curvature through Einstein's equations. This feedback is called back reaction. The original geometry shapes the quantum field. The altered quantum field carries energy and pressure. Those quantities then reshape the geometry that created them. A calculation that treats the bubble as permanently fixed leaves out this response. A self-consistent drive would need to remain stable after the quantum contribution was included. The 2009 work indicated that the studied superluminal geometry would probably fail that test. Growing energy near the white horizon could distort the bubble wall and prevent the configuration from remaining stationary for useful periods. This conclusion applied to a particular class of dynamically formed superluminal warp spacetimes. Other metrics can distribute curvature differently, so the result does not establish that every possible warp design must decay in exactly the same manner. It does reveal a separate barrier. Supplying the required negative energy would not guarantee that the resulting bubble could survive its own quantum environment. A stable geometry would need to form without producing destructive horizon effects, remain controllable throughout the journey, and release its stored curvature safely during shutdown. Even a bubble capable of meeting those demands would enter a deeper conflict with relativity. Superluminal motion allows different observers to assign different orders to departure and arrival, opening paths that can return information to an earlier time. The deeper conflict appears when the journey is viewed from more than one moving frame. Special relativity allows observers moving at different steady velocities to disagree about the timing of distant events. This is called the relativity of simultaneity. Two flashes that occur at the same moment for one observer may occur at different moments for another observer moving relative to the first. The disagreement becomes possible because there is no universal clock spread across the universe. Each observer builds a coordinate system using clocks in their own state of motion. Nearby events can be compared directly. Events separated by millions of kilometers require signals, and those signals can travel no faster than light. Ordinary causality remains protected inside that limit. Suppose a transmitter on Earth sends a light pulse toward a spacecraft. The pulse leaves first and arrives later. Every inertial observer may calculate different numerical times for the departure and arrival, but all of them agree about their order. The two events are connected by light, so the departure can influence the arrival. The same agreement holds for slower-than-light objects and signals. These connections lie inside what physicists call the light cone. A light cone maps the events that a flash of light can reach from one location, along with the events capable of sending light to that location. Events outside the cone are separated too widely for light to connect them in the available time. Their order can change between moving frames without causing a contradiction because neither event can influence the other. Faster-than-light travel would cross that protected boundary. Imagine two stations moving relative to one another. Station A sends a superluminal signal towards Station B. In A's coordinate system, the message departs at noon and arrives several minutes later. A different observer moving at a suitable velocity can calculate the same arrival as occurring before the departure. This result follows from the Lorentz transformation, the set of equations that converts positions and times between inertial frames. The transformation preserves the speed of light while mixing space and time. For ordinary signals, that mixing never reverses cause and effect. A superluminal connection can link events whose order is not fixed. A single reversed ordering does not yet create a message to the sender's own past. The loop closes when Station B immediately sends a faster-than-light reply using its own rest frame. Because the stations are moving relative to one another, B's definition of simultaneity differs from A's. With the correct separation, relative velocity, and superluminal signal speed, the reply can arrive at Station A before the original message was transmitted. This construction is called a tachyonic anti-telephone. A tachyon is a hypothetical faster-than-light particle, while an anti-telephone is a communication system capable of sending information backward in time. A pair of warp bubbles could replace the signals. One bubble carries a traveler outward, and another returns along a path defined in a differently moving frame. The complete route can form a closed time-like curve, meaning a future-directed path through space-time that eventually returns to an earlier event in its own history. Such a path creates familiar contradictions. A traveler could arrive early enough to prevent the departure that produced the journey. A message might contain information that was never originally created because it was copied from a future version of itself. Physics does not yet contain a confirmed rule explaining how every possible time loop would be prevented. In 1992, Stephen Hawking proposed the chronology protection conjecture. He suggested that quantum effects may grow strongly near the formation of a closed time-like curve and stop the region from becoming physically usable. The idea resembles the back reaction problem found near warp horizons. Quantum stress energy could rise as the geometry approaches a state that permits time travel, altering the spacetime before a complete loop forms. Chronology protection remains a conjecture. Testing it fully would require a reliable theory of quantum gravity, which physics does not yet possess. The connection between faster-than-light motion and backward time signaling therefore reaches beyond the machinery of one proposed drive. It comes from the structure of relativity itself. By the early 2020s, warp research had accumulated separate obstacles involving negative energy, quantum limits, causal horizons, instability, and chronology. Progress began to come from narrowing the goal and asking what kinds of warp geometry might remain physical below light speed. By 2021, a narrower approach had begun to reshape the field. Physicists Alexei Bobrik and Gianni Martire published a framework titled Introducing Physical Warp Drives. Their work treated warp drives as a broad family of space-time configurations rather than variations of Alcubierre's original bubble alone. The change in definition was important. A warp drive could be described as a shell of matter surrounding an interior passenger region. The shell's density, pressure, and motion determine how clocks and distances behave inside it. Different shell designs can create different relationships between the protected interior and the distant universe. The familiar Alcubierre bubble belongs to this wider family, although it occupies an extreme part of it. Its superluminal form requires negative energy and produces causal horizons. Bobrik and Martire examined whether slower configurations could retain some useful warp properties while remaining closer to known physics. Their model begins with spherical symmetry. In a perfectly spherical arrangement, the matter shell has the same general structure in every direction from its center. This simplification makes the equations easier to analyze and prevents directional features from being hidden inside an irregular shape. A passenger could remain in a central cavity surrounded by the shell. Depending on the chosen geometry, clocks inside that cavity might run at a different rate from clocks far outside. Distances and gravitational conditions could also be altered while the passenger remained separated from the densest matter. This broadened the meaning of warp travel. The term no longer had to describe a vessel crossing interstellar space faster than light. It could include any engineered shell that changed the space-time experienced by its occupants while moving through an external region. The framework also separated geometry from propulsion. A shell does not begin moving simply because its internal spacetime has unusual properties. If it already travels at a constant velocity, it can continue through inertial motion. Inertial motion means steady travel without acceleration, turning, or a change in speed. Changing that motion requires momentum to be exchanged. A conventional rocket accelerates by expelling propellant in the opposite direction. A light sail gains momentum from reflected photons. A gravitational assist changes a spacecraft's trajectory by exchanging a tiny amount of momentum with a moving planet. A warp shell remains subject to the same accounting. Its geometry may protect the passenger or alter internal clock rates, but the entire structure cannot accelerate itself from rest without interacting with something outside its center of mass. Bobrick and Martiret therefore described warp drives as transport shells rather than self-contained reactionless engines. A propulsion system would still be needed to launch the configuration, alter its velocity, and bring it to rest near a destination. This point changes how an interstellar mission must be evaluated. A metric can describe a shell moving at a chosen speed. It may say nothing about the energy required to reach that speed or the stresses created during acceleration. Within the slower-than-light category, the researchers identified configurations that could be supported by positive energy. The matter surrounding the passenger region could have an ordinary positive total mass, rather than the negative energy demanded by Alcubierre's superluminal wall. These subluminal designs could still produce recognizably warp-like effects. The passenger region might follow a geodesic through the constructed space-time. Proper time inside could differ from external time. The surrounding shell could shape the passenger's path without subjecting the interior to the same local conditions experienced by a conventional craft. The result created a clearer sequence for evaluating new proposals. The first task is to show that the space-time geometry solves Einstein's equations. The calculated stress energy must then be tested to determine whether a physically acceptable source could produce it. A complete transportation system must eventually explain construction, acceleration, steering, stability, and safe shutdown. Each stage can succeed, while the later stages remain unresolved. A positive energy subluminal shell therefore represents a genuine theoretical result without becoming an interstellar engine. It places part of warp drive mathematics inside the behavior permitted to ordinary matter while leaving the speed of light untouched. The apparent retreat produced a more useful research field. Physicists could now study protected passenger regions, material shells, and controlled space-time shifts without requiring every model to perform a superluminal journey. That boundary soon appeared less secure. During the same period, new calculations suggested that positive energy configurations might extend beyond light speed after all. That possibility gained attention in 2021, when several papers explored warp geometries that appeared to move beyond the familiar dependence on negative energy. One of the most discussed came from physicist Erich Lentz at the University of Göttingen in Germany. His paper, published in Classical and Quantum Gravity, described a class of superluminal structures called solitons. A soliton is a wave-like pattern that can travel while largely preserving its shape. Ordinary waves often spread out as they move. A soliton maintains a stable profile because the processes that would normally disperse it are balanced by non-linear effects within the system. Solitons appear in several areas of physics. They can form in shallow water, optical fibers, and certain plasmas. In each case, the moving pattern behaves more like a persistent object than a pulse that quickly fades. Lentz applied this concept to space-time. His construction used Einstein's equations together with gravitational, electromagnetic, and plasma fields. Plasma is a gas whose atoms have been separated into charged particles, allowing it to respond strongly to electric and magnetic fields. Stars contain plasma, and similar states can be produced in laboratories at far smaller scales. The proposed soliton was a compact pattern in spacetime that could move through an external region while carrying a protected interior. Its geometry differed from Alcubierre's original bubble, although the intended result was similar. A passenger region could be transported effectively faster than light, while remaining locally inside the rules of relativity. The most important claim concerned the source of the geometry. Lentz examined the energy density measured by a family of observers known as Eulerian observers. These observers remain aligned with the chosen slices of space used to describe the evolving geometry. They provide a natural reference frame for analyzing many warp drive metrics. In that frame, the calculated energy density appeared non-negative. This seemed to remove the requirement that had followed superluminal warp drives since 1994. The source could, in principle, be built from positive energy associated with gravitational, electromagnetic, and plasma fields, rather than a shell of exotic negative energy. The distinction was enormous. Positive energy exists throughout the known universe. It appears in matter, radiation, magnetic fields, and the motion of particles. A superluminal geometry supported entirely by positive energy would still be difficult to create, but its ingredients would belong to familiar physics. The scale remained extreme. Early estimates for a spacecraft-sized version involved mass energy comparable to astronomical objects. Some calculations placed the requirement near the mass of Jupiter or above, depending on the chosen geometry, wall dimensions, and speed. Jupiter contains about 1.9 times 10 to the 27 kilograms of mass. Converting even a fraction of that amount into a precisely arranged field would exceed all human energy production by an almost unimaginable margin. The energy associated with a single Jupiter mass is roughly 1.7 times 10 to the 44 joules, when calculated using mass multiplied by the speed of light squared. Positive energy, therefore, made the source less exotic without making the design practical. Humanity has no method for gathering planetary masses into a compact shell, shaping them into a moving soliton, or protecting passengers from the surrounding gravitational conditions. The scientific excitement came from the sign of the energy rather than the size of the engineering challenge. For decades, negative energy had appeared to be the clearest reason that superluminal warp drives could never be built from known matter. Lentz's paper seemed to show that the restriction might depend on the geometry researchers had chosen rather than on faster-than-light motion itself. Popular coverage often compressed this result into a simpler claim. Warp drive had become physically possible. A major theoretical barrier had fallen. Faster-than-light travel could be achieved using ordinary positive energy. The published work was more cautious. It presented a mathematical solution and identified conditions under which the selected observers measured non-negative energy density. It did not describe a reactor, construction method, or complete mission. The result still appeared to cross an important boundary. Bobrick and Martier had established a positive energy class below light speed. Lentz seemed to extend positive energy into the superluminal regime. That conclusion depended on the observers used to evaluate the stress energy. A physical energy condition must remain satisfied across a much wider range of possible motion through the same spacetime. Energy density in relativity depends partly on the observer measuring it. The stress-energy tensor contains the full local description of energy, pressure, stress, and momentum flow. To calculate the energy density seen by a particular observer, physicists combine that tensor with the observer's four velocity. A four velocity describes motion through both space and time. Two observers crossing the same region at different speeds can therefore assign different values to the energy density they encounter. The tensor remains the same. Their motion through it changes the measurement. A familiar comparison appears in electromagnetism. One observer may describe a situation mainly through an electric field, while another observer moving relative to the first measures a different mixture of electric and magnetic fields. Relativity connects those descriptions through a change of frame. Warp drive stress energy can behave in a similar way. An observer moving with the chosen spatial coordinates may measure positive energy in a region where another observer, passing through at a different velocity, measures a negative value. The Eulerian observers, used in many warp calculations, occupy a particularly convenient frame. They move perpendicular to the slices of space selected by the mathematical coordinate system. Their measurements make it easier to separate the geometry into space and time. Convenience does not give their frames special physical authority. The weak energy condition requires every physically allowed time-like observer to measure non-negative energy density. Checking one family of observers covers only part of that requirement. The null energy condition is broader in a different direction. It must hold along every permitted light-like direction through the region. In 2021, Jessica Santiago, Sebastian Schuster, and Matt Visser examined this limitation in detail. Their analysis considered generic warp-drive spacetimes within standard general relativity, rather than focusing only on one famous metric. They found that physically reasonable warp drives still violate the null energy condition. The result followed from the way a compact moving region must be embedded inside an exterior spacetime. Producing the required spatial flow creates combinations of momentum, density, and stress that become negative when tested along suitable light-like directions. A calculation centered on Eulerian energy density can miss those directions. The spacetime may appear acceptable when viewed by observers moving naturally with the chosen coordinates, while a light ray passing through at another angle reveals the violation. This distinction explains why the phrase positive energy can be incomplete. A geometry may have positive total mass. It may contain regions where selected observers measure positive density. It may still fail the weak or null energy condition somewhere else in the same structure. The Lentz soliton later received a more direct examination from physicists Bill Selmaster and Steve Rubin. In work released in 2025, they reconstructed parts of the proposed solution and reported negative energy regions that had not been removed by the original argument. Their analysis also identified problems in the derivation used to support the positive energy interpretation. Modified versions of the geometry continued to violate the weak energy condition. The correction reduced the strength of the 2021 claim. It did not erase the entire line of research. Lentz's work introduced new mathematical constructions, soliton-based methods, and ways of organizing warp geometries. Santiago, Schuster, Visser, Selmaster, and Rubin clarified how those constructions must be tested. This is a common pattern in theoretical physics. A proposed solution exposes a new region of the equations. Later researchers probe that region using stronger conditions and more complete calculations. The original result may narrow, while the field gains better tools for separating coordinate effects from physical ones. Warp drive research now required an observer-robust standard. A convincing solution had to survive tests across time-like motion and light-like directions throughout the geometry. Positive energy measured in one preferred frame could no longer carry the full claim. The 2024 team approached the problem from the opposite direction. They began with a stable shell possessing positive total mass, then introduced a limited warp-like shift and numerically tested how much of that effect the shell could support without crossing the classical energy condition boundaries. Their starting point was a massive spherical structure that already behaved acceptably under the classical tests of general relativity. The 2024 paper was led by physicist Jared Fuchs and developed with researchers connected to applied physics. Instead of beginning with an arbitrarily fast warp bubble and calculating whatever exotic source appeared, the team began with a positive mass shell designed to remain stable within the model. Spherical symmetry simplified the construction. Every point on the shell depended mainly on its distance from the center, allowing the researchers to calculate the density, pressure, momentum flow, and curvature throughout the structure. The worked example contained an empty central cavity with a radius of approximately 10 meters. A small spacecraft, or protected passenger compartment, could fit inside that region. The surrounding matter extended outward to a radius of about 20 meters, producing a shell roughly 10 meters thick. Its total mass was approximately 4.49 times 10 to the 27 kilograms. Jupiter has a mass of about 1.9 times 10 to the 27 kilograms, making the proposed shell roughly 2.36 times as massive as Jupiter. All of that mass was represented within a structure only 40 meters across from one outer edge to the other. The average density implied by those dimensions would be extraordinary. A sphere 20 meters in radius has a volume of only about 33,500 cubic meters. Even allowing for the empty cavity and a carefully varying density profile, the shell would contain planetary mass within the volume of a modest building. The paper did not identify a real substance capable of forming this object. Its importance came from the sign and behavior of the required energy. The shell possessed positive total mass rather than the negative mass associated with earlier superluminal bubbles. Physicists describe the mass measured from far outside an isolated spacetime using a quantity called ADM mass. The initials come from Richard Arnowit, Stanley Deser, and Charles Misner, who developed the formalism during the 20th century. A positive ADM mass means that a distant observer treats the entire configuration as an object with ordinary positive gravitational mass. The researchers then added the feature that made the shell a warp drive model. A controlled shift vector distribution was introduced around the passenger cavity. The shift vector describes how the spatial coordinates slide between successive moments. In this geometry, it changes the path followed by the central region relative to the distant exterior spacetime. A passenger near the center could follow a geodesic through the altered geometry. The surrounding shell would carry the cavity along its constructed path, while the passenger remained separated from the densest matter and strongest curvature. The strength of the shift had to remain limited. Increasing it changed the required momentum density and pressure inside the shell. Beyond a certain range, those quantities could cause one or more energy conditions to fail. The numerical example used a warp parameter corresponding to approximately 4% of light speed. 4% of light speed is close to 12,000 kilometers per second. Voyager 1 travels at roughly 17 kilometers per second relative to the Sun. The model's chosen speed was therefore about 700 times greater than Voyager 1's present outward velocity. It still remained far below the speed of light. The researchers evaluated the geometry using Warp Factory, a numerical toolkit created for studying warp spacetimes. The software calculates curvature from a selected metric, reconstructs the required stress-energy tensor, and tests the resulting energy density and pressures throughout a numerical grid. The weak, null, strong, and dominant energy conditions were checked within the constructed model. All four remained satisfied for the selected shell and shift parameters. That result separated the solution from the Alcubierre bubble and the later superluminal proposals that appeared positive only in a preferred frame. The Fuchs configuration combined positive total mass with a real shift effect while remaining within the classical energy condition boundaries tested by the software. The word physical, therefore, has a specific meaning here. The model does not require negative energy under its stated assumptions, and its stress energy behaves acceptably within classical general relativity. It remains a numerical spacetime rather than a material recipe, propulsion system, or construction plan. Its greatest strength and its most important limitation come from the same design choice. The warp effect remains physically controlled because the model never crosses the speed of light. That boundary is contained in the word subluminal. The term comes from the Latin word lumen, meaning light. In physics, subluminal motion remains below the speed of light. Superluminal motion exceeds it. The Fuchs model belongs entirely to the first category. Its worked example uses a shift corresponding to about 4% of light speed. Light travels through a vacuum at nearly 300,000 kilometers per second, placing the model's speed close to 12,000 kilometers per second. That velocity would transform space travel within the solar system, A spacecraft maintaining it could cross the average distance between Earth and the Moon in roughly 32 seconds. Mars can approach within about 55 million kilometers of Earth, although the actual distance changes constantly as both planets orbit. At 12,000 kilometers per second, that minimum separation would take a little over 1 hour to cross, ignoring acceleration and the need to match Mars's motion. The distances between stars remain much larger. Proxima Centauri lies about 4.25 light-years away. A craft traveling steadily at 4% of light speed would cover 4/100ths of a light-year during each Earth year. Dividing the full distance by that rate gives a journey of approximately 106 years. That estimate assumes the craft begins the voyage already traveling at its cruising speed and stops instantly at the destination. A real mission would need time and distance for acceleration, followed by a braking phase near Proxima Centauri. Both would lengthen the trip. A departure in 2026 would therefore produce an arrival around the early 2130s, under the most simplified calculation. Most people alive at launch would never see the destination reached. Relativity would provide almost no relief at this speed. The Lorentz factor at 4% of light speed is approximately 1.0008. A passenger experiencing 100 years aboard the craft would differ from Earth's elapsed time by only a small fraction of a year. The precise difference would depend on the acceleration history and the exact cruise duration, although it would amount to weeks rather than generations. Significant time dilation appears much closer to light speed. At 90% of light speed, the Lorentz factor rises above 2. At 99%, it exceeds 7. 4% remains within a range where onboard clocks and distant Earth clocks advance at nearly the same rate. The warp geometry could still change the conditions experienced by the passengers. In the model, the central cavity follows a geodesic through the constructed spacetime. A geodesic is the natural free-falling path permitted by the surrounding geometry. Passengers near the center could remain separated from the shell's strongest density and curvature, while the complete structure moved through the external region. This arrangement could matter during acceleration if a future dynamic version preserved the protected interior. Conventional rockets transfer force through the vehicle. Engines push against the spacecraft structure, seats push against the passengers, and internal components must withstand the resulting load. A carefully controlled warp-like geometry might allow the central region to follow a smoother path. That possibility remains theoretical, because the 2024 solution describes constant velocity rather than a complete acceleration process. The geometry also does not erase the external distance. Proxima Centauri remains 4.25 light-years from Earth, and the bubble still takes more than a century to cross that separation at the modeled speed. This distinction defines the real achievement. The paper demonstrates that negative energy is not required for every space-time configuration that can reasonably be described as a warp drive. Positive mass can surround a protected cavity, and a controlled shift can produce genuine geodesic transport while satisfying the tested classical energy conditions. No accepted positive energy model has yet produced a controllable journey beyond light speed. Superluminal versions continue to encounter negative energy requirements, observer-dependent violations, causal horizons, quantum instability, and the possibility of closed time-like curves. The discovery, therefore, occupies a narrow but meaningful part of the theory. Warp geometry has moved closer to ordinary matter. Faster-than-light transportation remains outside the result. Even the slower model begins its calculation with more than 2 Jupiter masses already moving at nearly 12,000 kilometers per second. A complete vehicle would still need a way to create that shell, accelerate it, guide it across interstellar space, and bring it safely to rest. A complete interstellar mission would begin long before the century-long cruise. The matter required for the shell would first have to be gathered and shaped into the correct density profile. A protected cavity would need to remain open at the center while the surrounding mass settled into a stable configuration. The complete structure would then have to accelerate, hold its geometry during travel, adjust its course, slow near the destination, and eventually release its passengers without collapsing inward. The 2024 model describes only the constant velocity portion of that sequence. Constant velocity means steady motion in a straight line, with no change in speed or direction. The calculation begins with the shell already traveling at the selected rate. It does not describe a stationary structure being switched on near Earth and gradually accelerated to 4% of light speed. That missing history matters because acceleration requires momentum. Momentum measures how difficult it is to change an object's motion. A small spacecraft can gain momentum by ejecting propellant backward. A solar sail receives momentum from reflected sunlight. A probe passing a planet can exchange momentum through gravity, altering its speed and direction, while the planet experiences a far smaller change. A warp shell must follow the same conservation law. Its center of mass cannot begin accelerating through empty space without transferring an equal amount of momentum somewhere else. Radiation could carry that momentum. Expelled matter could carry it. A gravitational interaction with another massive body could change it. The geometry alone does not provide a free source. The amount involved in the Fuchs example is difficult to overstate. The shell has a mass of approximately 4.49 times 10 to the 27 kilograms. 4% of light speed is close to 12 million meters per second. Accelerating that mass, from rest to the modeled cruise speed, would require roughly 3.2 times 10 to the 41 joules of kinetic energy. That estimate assumes ideal conversion with no wasted energy. It excludes the energy needed to collect the matter, compress it into the required profile, maintain the cavity, and later slow the structure again. The Sun produces about 3.8 times 10 to the 26 joules of energy each second. At that steady rate, generating the shell's cruise energy would require approximately 27 million years of the Sun's entire output. Braking near Proxima Centauri would require removing a comparable amount of kinetic energy. That energy would need to leave through radiation, expelled mass, interaction with an external field, or some other physical process. Releasing it carelessly near a planetary system would create an event far beyond ordinary engineering hazards. Acceleration would also place new stresses on the shell. The density and pressure distribution that remains stable at constant velocity may change when different parts of the structure begin moving at slightly different rates. The front cannot respond before information reaches it, so any controlled change must propagate through the material or field at a finite speed. A poorly coordinated acceleration could distort the cavity, produce oscillations in the shell, or push parts of the stress-energy tensor beyond the energy conditions the original model satisfied. Interstellar matter adds another burden. Space between the stars is extremely thin, often containing around 1 atom in each cubic centimeter, although the density varies greatly between regions. Across several light years, even that sparse material becomes a continuous stream of impacts. At 4% of light speed, a grain of dust weighing 1 gram would carry roughly 72 billion joules of kinetic energy relative to the spacecraft. That is comparable to the explosive energy of more than 17 tons of TNT. Smaller particles would arrive more often and could produce radiation, erosion, and heat in the leading shell. Navigation would require equally careful control. Proxima Centauri moves through space while the voyage is underway. A prediction extending more than a century into the future would need to account for the motion of all 3 stars in the Alpha Centauri system, their gravitational interactions, and any correction required during flight. The model provides no steering system for making those corrections. Safe arrival would demand a stable deceleration phase, followed by a controlled transition back to ordinary spacetime. The passengers would need to emerge with a velocity appropriate for the destination system, rather than continuing through it at 12,000 kilometers per second. The 2024 solution, therefore, describes an important cruise state. The launch, steering, braking, and shutdown remain separate physical problems whose energy and momentum cannot be removed by the warp label. Newer models have begun exploring those missing stages. Their approach accepts the conservation laws directly, using radiation and mass loss to pay for every change in motion. One such attempt appeared in June of 2026, when physicist Ann T. Ley released a preprint titled "Steering a Warp Drive Without Exotic Matter." A preprint is a scientific paper shared publicly before the journal review process has been completed, so its conclusions remain open to further examination. The model begins with a strict conservation law. An isolated object cannot accelerate its center of mass without transferring momentum elsewhere. A rocket sends propellant backward. A light sail receives momentum from incoming photons. A warp-like shell, built from positive energy, must also exchange momentum with its surroundings whenever it changes speed or direction. The proposed drive handles that requirement through radiation. Photons have no rest mass, yet they carry both energy and momentum. When a beam of light is emitted in one direction, the source recoils in the opposite direction. This is the operating principle of a photon rocket. The amount of thrust is found by dividing the beam's power by the speed of light. A perfectly directed beam, carrying 300 million watts, would produce only about 1 Newton of thrust. 1 Newton is roughly the force needed to support a small apple against Earth's gravity. A 1 gigawatt beam would provide about 3.3 newtons. That beam would carry as much power as a large electrical generating station while producing less thrust than many handheld rocket engines. The enormous power requirement comes from the absence of massive exhaust. Ordinary propellant can carry large momentum at speeds far below light. Photons travel at light speed and provide the greatest possible momentum for a given amount of expelled mass, although converting stored mass into a sufficiently intense directed beam remains extremely costly. Ley's construction uses an exact solution known as the Kinnersley photon rocket for the exterior spacetime. This geometry describes an object accelerating because it emits radiation unevenly. More radiation leaves one side, producing recoil toward the other. Inside that radiating exterior, the model places a time-like shell surrounding an exactly flat cavity. Time-like means that ordinary clocks and passengers can move through the cavity along paths below light speed. The central region is protected from tidal distortion, allowing its occupants to experience locally flat spacetime while the surrounding shell follows an accelerating trajectory. The geometry is matched across the shell so that the flat interior and radiating exterior fit together consistently within Einstein's equations. The exterior solution and steering law are exact. The shell's physical behavior was tested through perturbative calculations and numerical methods. As the craft emits photons, its total mass energy decreases. Far from an isolated radiating object, this changing quantity is described by the Bondi mass. It represents the mass remaining after outgoing radiation has carried energy away toward distant space. Every steering maneuver, therefore, has a measurable cost. Stronger acceleration demands a faster loss of Bondi mass. Longer burns continue reducing the energy available to the system. The paper also finds limits connected with compactness, which compares an object's mass with its radius. Packing too much mass into too small a shell brings the structure closer to forming a horizon. Within the model, acceptable accelerating shells exist only inside a restricted range of size, mass, and acceleration. The surface shell can satisfy the dominant energy condition for suitable parameters. That condition requires the local energy density to remain non-negative, while energy and momentum flow causally through the material. The drive remains slower than light throughout the construction. Its motion obeys ordinary causal order, and its acceleration comes from photon recoil rather than a self-propelling distortion of spacetime. Stability also remains incomplete. The paper identifies configurations that are marginally stable and suggests that stricter stability may be possible without violating the energy conditions. A full simulation coupling the changing radiation, shell motion, and internal stresses over an extended journey has not yet been completed. The result describes a theoretical model rather than a practical engine. It consumes mass energy, produces limited thrust for immense power, and never crosses the speed of light. Its protected cavity still gives the system a warp-like feature. Passengers occupy an unusually calm region while the exterior structure accelerates around them. This direction of research accepts the energy and momentum costs openly. Progress comes from constructing geometries that follow conservation laws while shielding the interior from some effects of acceleration. Evaluating such designs requires more than checking the energy measured by one convenient observer. Modern numerical tools can search through many directions and velocities, revealing physical violations that a single reference frame may leave hidden. The required test now involves far more than reading a few equations at selected points. Warp drive metrics can contain energy density, pressure, momentum flow, and shear mixed together inside the same stress-energy tensor. Some of these quantities appear in off-diagonal terms, which describe relationships between different directions rather than simple values along one axis. As the geometry becomes more complex, an analytical calculation may remain possible only after simplifying the shape or choosing a particularly convenient observer. Those shortcuts can hide important behavior. In 2024, researchers at Applied Physics introduced a numerical toolkit called Warp Factory. It was designed to calculate general warp geometries across a three-dimensional grid rather than limiting the analysis to metrics simple enough to solve entirely by hand. The program begins with a proposed metric. It calculates the curvature associated with that geometry, then uses Einstein's equations to reconstruct the required stress-energy tensor. Energy conditions can be tested at thousands or millions of points throughout the model. Warp Factory also produces two-dimensional slices and three-dimensional visualizations. A researcher can see where negative energy appears, where pressure becomes extreme, and how the pattern changes when the bubble radius or wall profile is adjusted. This makes geometric optimization more systematic. The computer can alter selected parameters and search for configurations with lower energy requirements or smaller violations. A design that looks promising can then be examined more closely. The original Warp Factory analysis still relied on a limited set of observer directions in parts of its energy condition testing. A newer, open-source system called WarpAx was introduced in 2026 to make that search more observer-robust. WarpAx uses graphics processing hardware to evaluate large numbers of calculations in parallel. The same processors developed for rendering images and training artificial intelligence models can also examine many possible paths through a spacetime. At each sampled location, the program changes the observer's direction and rapidity. Rapidity is a relativistic way of describing velocity. It grows smoothly as an observer approaches light speed and works conveniently inside Lorentz transformations. The software searches for the observer who measures the most severe energy condition violation at that point. A geometry passes only when every physically relevant direction survives the test. This approach differs from checking a stationary Eulerian observer alone. An Eulerian observer may move naturally with the chosen coordinate slices and measure positive energy. A second observer, traveling through the same region at high speed or along another direction, may encounter a combination of energy and momentum that becomes negative. Warpax also classifies the stress-energy tensor using the Hawking-Ellis system. This classification groups tensors according to the kinds of eigenvectors they possess and the way energy flows through spacetime. An eigenvector is a direction that retains its orientation when a mathematical transformation is applied. In this setting, it helps identify whether the stress energy resembles ordinary matter, a directed beam of radiation, or a more unusual structure. More than 96% of the tested grid points across the studied metrics belong to Hawking-Ellis Type 1. At those points, the energy conditions could be checked exactly through algebraic relationships between density and pressure. The result did not depend on how many observer directions happened to be sampled. The toolkit was applied to the Alcubierre, Lentz, Van den Broek, Notario, and Rodel metrics, along with a separate shell geometry used as a numerical test. The Rodel metric provided a clear example of what a single frame can miss. A standard Eulerian analysis failed to identify dominant energy condition violations at more than 28% of the tested grid points. Weak energy condition violations were missed at more than 15%. Even when the location of a violation was already known, its strength could be greatly underestimated. In the Alcubierre geometry, optimizing over observer motion produced a weak energy condition violation roughly 90,000 times more severe than the Eulerian value at the selected rapidity limit. These calculations do not prove that every possible future geometry must fail. They show that claims of physicality now face a much more demanding standard. Positive energy in one frame supplies only an early result. The full tensor must remain acceptable across the motions and directions available within the spacetime. Every superluminal metric examined with these methods continues to show major physical difficulties. Numerical tools are narrowing the places where an unnoticed solution might hide. A grid still captures the geometry at selected moments. Allowing that geometry to evolve through time opens a different form of investigation. Researchers can simulate the formation of a bubble, disturb its supporting structure, and calculate the signal produced when the warped region collapses. Once a warped geometry is allowed to change with time, the equations can follow its failure as well as its motion. In 2024, physicists Katie Clough, Tim Dietrich, and Sebastian Kahn used numerical relativity to study what might happen when an Alcubierre-like containment structure becomes unstable. Their model did not assume that a bubble could be built with known technology. It treated the proposed spacetime as an initial condition and asked how that geometry would evolve after its support began to fail. Numerical relativity is the same broad method used to simulate black hole mergers and neutron-star collisions. Einstein's equations are too complicated to solve exactly during many violent changing events. Researchers divide space into a computational grid, calculate the geometry at one moment, and then advance the solution through a sequence of very small time steps. At each step, the program tracks how curvature changes across the grid. It also follows the motion of the assumed matter or energy source and checks how those changes affect the surrounding spacetime. The warp drive simulation began with a localized region resembling an Alcubierre bubble. The supporting material was represented through a fluid model with unusual properties. Once the configuration lost containment, the curved region could no longer preserve its original form. The bubble began to collapse. As the supporting structure changed, the distribution of curvature shifted rapidly. Part of the distorted spacetime relaxed inward, and part propagated away from the source. Changing curvature can produce gravitational waves. A gravitational wave is a traveling disturbance in spacetime. It stretches one direction while compressing another by an extremely small amount. Detectors such as the Laser Interferometer Gravitational Wave Observatory measure these effects by comparing the lengths of long perpendicular arms with laser light. The first directly detected signal, recorded in September of 2015, came from two black holes merging about 1.3 billion light-years away. That event briefly released several solar masses of energy as gravitational radiation. A collapsing warp bubble would involve a very different source. The signal would come from the rapid rearrangement of an engineered region of curvature rather than two orbiting compact objects. The simulation allowed the researchers to calculate a waveform. A waveform records how the strength of a gravitational signal changes with time. Its shape can contain information about the source's size, symmetry, collapse rate, and internal structure. The predicted signal depended strongly on the assumptions placed into the model. A larger bubble would affect a greater volume of space-time. A faster collapse would push more power toward higher frequencies. Different wall profiles and energy distributions would produce different patterns. The bubble scale used in a calculation also determines whether any signal would fall inside the range of existing detectors. Ground-based observatories are most sensitive to frequencies from roughly tens of hertz to a few thousand hertz. Space-based detectors planned for the future will target much lower frequencies associated with larger and slower systems. A hypothetical warp structure could therefore produce a signal outside the range of every instrument currently operating. Its strength would also fall with distance, and an unfamiliar waveform could be confused with noise or with a conventional astrophysical event that had not yet been modeled correctly. No gravitational wave observatory has detected evidence of a warp drive. Using such a waveform as a technosignature remains highly speculative. A technosignature is an observable sign that may have been produced by technology rather than by a natural process. Before any unusual signal could support that interpretation, researchers would need to rule out black holes, neutron stars, stellar collapse, instrumental effects, and other known sources. The more immediate value of the study lies in dynamics. Earlier warp calculations often treated the geometry as fixed and permanent. A collapse simulation shows how stored curvature might move, disperse, and release energy when the structure changes. It also reveals whether the assumed matter distribution remains stable long enough to support the bubble. Even a geometry that passes a static energy condition test may behave very differently when disturbed. Small errors can grow. Pressure can redistribute. Curvature can travel outward as radiation. Warp research has therefore moved beyond asking whether a metric can be written down. It can now test how a proposed spacetime responds when its supporting structure fails. That progress sharpens the final conclusion. The mathematics of warp geometry has become more detailed and more physically disciplined. A complete faster-than-light vehicle still remains absent from every stage required for a real journey. The answer can now be stated clearly. Scientists have not discovered a complete physical method for traveling faster than light. The strongest positive energy warp models remain below the speed of light, and every studied superluminal design still carries major problems involving energy, control, stability, or causality. The 2024 Fuchs solution is a genuine advance. It describes a spherical shell with positive total mass surrounding a protected passenger cavity. A controlled shift in the geometry carries that central region along a geodesic, while the model satisfies the classical energy conditions tested in the calculation. Its mass is about 4.49 times 10 to the 27 kilograms. Its worked speed is roughly 4% of light speed. A journey to Proxima Centauri would still take approximately 106 years before adding acceleration and braking. The result changes what physicists can say about warp drives. A warp-like spacetime can be supported by positive mass under carefully chosen subluminal conditions. Passengers can occupy a relatively calm central region. Numerical tools can test the required stress energy across large grids, and search through many possible observer motions. The field has also developed broader classifications of warp geometry. Researchers can compare Alcubierre bubbles, soliton models, enlarged interiors, zero expansion metrics, positive mass shells, and radiating steerable cavities within a shared framework. Dynamic simulations add another level. A proposed bubble can now be disturbed and evolved through time, allowing physicists to calculate how curvature moves and what gravitational radiation might be released during collapse. Each advance solves only one layer of the complete transportation problem. A mathematical metric establishes that a geometry can be written inside Einstein's equations. The calculated stress energy then determines whether any acceptable source could create it. Stability analysis asks whether the structure can survive small disturbances and its own quantum effects. Engineering begins after those tests. The required matter must be gathered, arranged, accelerated, steered, slowed, and safely dismantled. Momentum must be transferred somewhere during every change in motion. Waste energy must leave without destroying the spacecraft or its destination. A superluminal mission introduces further requirements. The front of the bubble must remain controllable after causal horizons appear. Quantum fields must avoid producing destructive stress near those horizons. The complete route must also preserve the order of cause and effect rather than forming a closed time-like curve. A future paper capable of changing the answer would need to address this full sequence. It would describe an evolving spacetime that begins from physically ordinary conditions. Its source would use positive, producible energy at a manageable scale. The geometry would accelerate from rest, respond to steering commands, and decelerate near a destination while remaining stable. The passengers would need protection from tidal forces, radiation, and impacts with interstellar matter. The full stress energy tensor would need to satisfy robust tests across all permitted observers and light-like directions. Quantum back reaction would have to remain controlled throughout the journey. Effective travel beyond light speed would also need to occur without allowing information or passengers to return to their own past. No current model meets that standard. Einstein's equations still describe a universe with remarkable geometric freedom. They allow clocks to run at different rates, light to curve around galaxies, gravitational waves to cross billions of light years, and expanding space to separate distant regions faster than light could cross the growing distance. The same equations also connect every engineered curvature to energy, pressure, and momentum. As warp geometries move closer to matter known by physics, they remain on the slower side of the light boundary. This leaves humanity with difficult forms of interstellar travel. Laser-driven probes may cross the nearest stellar distance within several decades. Crewed vessels would require powerful propulsion, extensive shielding, and life support systems capable of operating for generations. Relativistic journeys could shorten the time experienced by passengers, although the energy requirement would rise dramatically near light speed. The luminous distortion surrounding an imagined spacecraft represents a geometry that relativity can describe. It has not become a proven road to another star. Between that image and Proxima Centauri remain planetary masses, quantum restrictions, causal horizons, and more than 4 light-years of real distance. Warp drive research has moved closer to physical reality. Faster-than-light travel remains beyond every complete solution currently known.